Chapter 6.42, Vectors and Dot Products. We're going to take a look at writing a vector as a sum of two vector components and use vectors to determine the work done by a force. So the definition of vector component, so let u and v be non-zero vectors such that u equals w1 and w2. So we know we have these, we've done this before. We add them together and we find that the resultant is this here. U. So W1 and W2 are orthogonal, and W1 is parallel to or a scalar multiple of V. So you see here's V and here's W1, and it's just a little longer. The vectors W1 and W2 are vector components of U. Vector W1 is a projection of U onto V. Okay, so U onto V, and is denoted by W1 equals a projection of V and then U. The vector W2 is given by W2, so W2 equals U minus W1. So the projection of U onto V, this is the formula that we're going to use. Let U and V be non-zero vectors. The projection of U onto V is given by, parentheses, U times V over the magnitude of V squared times V. And so we'll use that to try some examples here. So decomposing a vector into components. So find the projection of U, 3, negative 5, onto V, 6, 2. Then write U as a sum of the two orthogonal vectors, one of which is projection of V onto U. So we're going to use that formula. So W1 equals the projection of VU equals U times V over the magnitude of V squared times V. So we're going to multiply U and V. So let's do 3, negative 5 times 6, 2, all over, and this is going to be the square root of 6 squared plus 2 squared, but then that is squared, and then times V, which is 6, 2. So this is going to be, so just to remember I'm multiplying, this is 3 times 6, plus a negative 5 times 2 over 6 times 6 is 36, plus 4 is square root of 40 squared, which is just 40, and then times 6, 2. So this is 18 minus 10, so this ends up being 8 over 40, 6, 2, or 1 over 5, 6, 2. So this is our W1. And then the book will leave it like this. We could also multiply it through, and if we did, we would get 6 over 5 and 2 over 5. But I know, like WebAssign might just leave it in this form. So that's our W1. So I'm going to leave it in this form for now. And then we need to find W2. So W2 is going to be U minus W1. So U is 3, negative 5, and then minus the 6 fifths and 2 fifths. So we need a common denominator, so I'm going to multiply by 5 over 5 to both. So this is going to be 15 over 5 and negative 25 over 5. Then we're going to subtract minus 6 over 5 and 2 fifths. So 15 minus 6 is 9 over 5, and negative 25 minus 2 is negative 27 over 5. So that is our W2. Now the last part is to write U as a sum of two orthogonal vectors. So we're going to add together our W1 and W2. And so notice when we add them together what we get. We get 6 over 5 and 2 over 5 plus 9 over 5 and negative 27 over 5. So this is going to be 15 over 5 and negative 25 over 5. And notice this simplifies to 3, comma, negative 5, which is what we had in the very beginning. So try this out. Find the projection of u 3, 4 onto v, 8, 2. Then write u as the sum of two orthogonal vectors, one of which is projection v, u. Okay, so trying this out, you should have gotten 1, 17, 64, 16. So you could write it in this way. It's what it does in the book. Or you can distribute it, and the 17 can be in the denominator. Then W2 is u minus W1. And then so I multiply by 17 over 17. And so I multiply the 17 inside. And I get 51 and 68 and still 1/17. Then I subtract. So I get negative 13. It could be negative 13 over 17 and 52 over 17. Then to prove or write the sum as two orthogonal vectors, so we're going to add W1 and W2 together, and you notice you get your u back 3, 4.